Quicksort is the last sorting algorithm that we're going to explore in real detail. And as I indicated in the previous lecture, Quicksort has certain commonality with Mergesort in that both approaches use divide and conquer strategy, and both algorithms are usually implemented using recursion. So, like Mergesort, Quicksort uses this idea of chopping the array that you want to sort into two parts. That's what's similar between Quicksort and Mergesort, but after that, they differ really radically. Okay? We're going to eventually test all these sorting algorithms, and actually we'll find out that at least the way I've implemented the code, Quicksort becomes the clear winner usually once you start sorting arrays of any substantial size. Quicksort and Mergesort will both do much, much better than bubble sort and selection sort and insertion sort. But usually Quicksort does a little bit better than Mergesort. But there's some subtleties to this, and we'll get into that later. Okay, Quicksort does sort in place, unlike Mergesort. So the meaning of that is that Quicksort doesn't require an auxiliary array or a lot of extra memory. A downside to Quicksort is that although Quicksort does work recursively, does use a divide and conquer strategy, and does split the original array into two parts, unlike Mergesort, we cannot be, we have no assurance really that the two parts are nearly equal size. Okay, in Mergesort, remember, it's actually very definite objective to take a portion of the array that you're trying to sort and chop it into two halves that are either equal size or nearly equal size. Well, we'd like that to be the case for Quicksort, but we're going to find out that we can't really have any, there's no reasonable way to be assured that the two halves, if you will, are really equal size or nearly equal size. In the case of Quicksort, it's going to turn out that we split the entire array into two parts. And after sorting each part, the array as a whole will be sorted. Now that probably comes as a surprise. That certainly was not true of Mergesort. With Mergesort, we had to do the extra work and merge the two halves together. But with Quicksort, we're going to do some processing, some work before making the recursive calls to sort the two parts. Okay? Specifically, what we're going to do is we're going to work to make sure that every entry in the first part is less than every entry in the second part. Okay? So if we can set that up, if we can be assured that each entry in the first half is less than each entry in the second half, then when we sort the first half and then sort the second half, well then it's obvious that the entire array will be sorted. Okay, so think about that. And here again, let's be careful. I'm sorry that I'm saying half, maybe, because I don't mean to imply that the two halves are the same size. Again, that's the downside to Quicksort. We have split the array into two parts, which I'll call halves, but they may not be equal sized, or they might not even be close to equal sized. Okay? In order to arrange that all of the entries are in the all of the entries in the first part are less than all the entries in the second part, the traditional way to do that is to select one of the entries in the array to play the role of a pivot. Okay, there are a number of variations of quicksort, but usually what happens is some entry in the array plays the role of a pivot. Okay, and then what you do is arrange for all the numbers that are less than or equal to the pivot to occur in the array before all of the entries that are greater than the pivot. Okay? In the specific code that I will present later, the role of the pivot will be played by the entry in the rightmost position. Okay, the last entry will be the pivot. And then we can implement quicksort by simply scanning from left to right, and anytime we come upon an entry that is less than or equal to the pivot, we do a swap to make sure that it occurs before entries that are greater than the pivot. We'll get into nitty-gritty of this pretty soon with an example. So trusting that this is going to work, and we'll have split the array into two subarrays, with everything in the first subarray being less than or equal to the pivot, and everything in the second subarray being greater than the pivot. Then, as I said before, if we just now recursively sort each of those parts, the entire array will be sorted. Here's an example. Once again, people implement quicksort in slightly different ways. There are different versions. But here is a popular version. I'm going to use two arrows, a black arrow that is simply going to proceed from left to right, take a single pass through this array. And as we go along, there's going to be this red arrow, and the red arrow is going to mark the end of the first subarray. Okay, reminding you that everything in the first subarray, we want it to be less than or equal to the pivot. Okay, so what is the pivot in this example? Well, again, I'm using the last entry as the pivot. So in this example, 21 will play the role of the pivot. Okay, let's examine the first entry. The black arrow is currently pointing to 63. Is that greater than the pivot, or is it less than or equal to the pivot? Well, it's greater than the pivot. Okay, since 63 is greater than the pivot, we just move the right arrow along. Oh, I forgot to mention that the red arrow is initially pointed before the array. Okay, now we're looking at the next entry in the array, which is 17. Is that greater than the pivot, or is it less than or equal to the pivot? Well, of course, it's less than or equal to the pivot. 17 is less than 21. So therefore, 17 belongs in the first portion, the first subarray. So what we're going to do is we're going to advance the red arrow, move it to the right, and then swap 17 with whatever the red arrow is pointing to. So once we move the red arrow to the right, it'll be pointing to 63, and we're going to swap 17 and 63. All right, and now it's time to move on. So we advance the right arrow. We'll be looking at 92. And let's see, 92 is greater than the pivot, so we move on. We advance the right pointer again. So now we examine the next entry, which is 5, and we see that this is less than the pivot. Okay, so 5 belongs in the first portion of the array. And we're going to have to do a swap in order to get it there. Okay, specifically, we advance the red arrow so that it points to 63, and then we swap the 63 and the 5. Okay? So there's the situation after the swap. And take a little pause and notice what we've got so far. So the entries from the beginning of the array up to the red arrow are all less than the pivot. And the entries after that up to the black arrow are all greater than the pivot. That's what we want. Well, everything up to the red arrow is less than or equal to the pivot. And everything after the arrow up to the black arrow is greater than the pivot. Let's continue. So we advance the black arrow, and we'll be pointing at 72. Well, 72 is bigger than the pivot, so we just advance the black arrow again, and now it'll be pointing to 21. And of course, we're at the end of the array now. When we examine 21, we see that it is less than or equal to the pivot, and therefore we have to do a swap again. Okay? Since since 21 is greater than or equal to, since 21 is less than or equal to the pivot, we do a swap. We'll have to advance the red arrow again and swap what's there, which is 92, with 21. Okay? So I think you see in this figure here, the red arrow was pointing to 92, the black arrow was pointing to 21, and they just got swapped, and so now we're pretty much done with this this part of Quicksort, because everything from the beginning of the array up to the red arrow is less than or equal to the pivot. Everything after that is greater than the pivot. Okay, we have the two portions of the array. We got lucky. They actually have the same size. Okay, the first portion is 17, 5, and 21, and the second portion is 63, 72, 82. So we got lucky and had an even split here. Both subarrays have size 3. But in general, that's not going to happen. We can't expect the two subarrays to have the same size. Okay, if we make a recursive call, then these two subarrays will be sorted. And once we sort each of these two subarrays, the entire array will be sorted. There it is. Sort the first half and you get 5, 17, 21. Sort the second half and you get 63, 72, 92. And because we ensure that everything in the first half is less than everything in the second half, the entire array is now sorted. Okay, just as we said with Mergesort, it's important to realize that the split here is purely conceptual. I actually separate the two parts in the figure here, but in reality, we're not really splitting the array or moving data around. I mean, we are swapping entries in the array, but we're not doing other than that. All right, so Quicksort uses a divide and conquer strategy, much like Mergesort uses a divide and conquer strategy, and so it's natural and relatively easy to implement Quicksort by means of a recursive function, and that's what we're going to do. We have to be careful how we write the recursive function, but I guess I want to stress again, as you're getting used to recursion, when you make a recursive call, you kind of have to trust that it's going to do what it's supposed to do. If you code everything else correctly, then it'll do its job. So let's get into it and take a look at the Quicksort code that is part of the sorting code provided at the course site. In a little while, I'm going to actually want to make sure that you experience all of these sorting algorithms running, and we will be comparing them. But if you haven't done so already, you might consider downloading the sorting code and getting it running at this point. So here's the code for Quicksort. I actually have two different functions named Quicksort here. At the top, there's a Quicksort that has a single parameter, which is the array that we want to sort. And at the bottom, there's a Quicksort function that has 3 parameters. And it is this function that kind of matches the Mergesort function that we looked at previously. This 3-parameter Quicksort is going to be a recursive function, and it's used to sort a portion of the array, namely the subarray that begins at index left and ends at index right. Okay? And in a little while we'll get into the nitty-gritty of this and see the recursive calls. But first let's look at the Quicksort function above that, the 1-parameter Quicksort. And I just point out that this is a very simple thing. This is a non-recursive function that uses the 3-parameter recursive function to sort the entire array. Okay? What I'm doing here is I'm assuming that size has already been set previously, a global variable, to equal the length of the array. Okay? The way this is actually implemented in my code, it differs slightly from Java to C++. It's a minor detail. Let's not worry about it. Okay, but there is this 1-parameter Quicksort for the purpose of sorting the entire array. Frankly, I also have a similar 1-parameter, well, not quite 2-parameter version of Mergesort, but I didn't discuss it in the lecture notes, but you'll see it when you download the code. All right, we're going to start looking at the details of the 3-parameter recursive Quicksort function now. This begins with the declaration of a few local variables, and we see that 2 of these local variables are of type double, and that's because I've written this code to sort an array of doubles. Okay, so one of these variables is named pivot, and you can guess that that is going to be set to the value of the pivot while we do the Quicksort. Temp is going to be used to help do swapping. When we need to swap 2 entries in the array, we'll use temp. Okay, now what about I and j? I and j are int, and they are going to be used as indexes into arrays, into the array. Well, now this is going to be very simple conceptually, similar to what happened with Mergesort. I and j are going to correspond to the arrows that we used in the figures when we went through the example. Okay? Specifically, I plays the role of the red arrow, and j plays the role of black arrow. Okay? So as we proceed through this code, j is simply going to get incremented steadily to take a single pass through the subarray that we're trying to sort, and I is going to keep track of the end of the first half subdivision of that. Okay? So the action now begins with the statement if parentheses less than left less than right parentheses curly brackets, and a whole bunch of stuff that is inside curly brackets that we're going to see some of it in the next slide. Well, this is just like it was with Mergesort. Okay? If left is equal to right, then the subarray we're trying to sort consists of a single number and therefore is already sorted, so there's no work to be done. Okay, so we only want to do some work if left is less than right. Okay, assuming that's the case, the first thing that's done here is that whatever is in position right of the array gets copied into pivot. That's exactly in line with what we were saying in the example. We take whatever is furthest to the right and put it into pivot. Okay? Also, I, which corresponds to the red arrow, is initially set to 1 less than left. Okay, since it's set to 1 less than left, it's actually, if you like, that the red arrow is pointing just before the portion of the array that we're trying to sort. And now we've pretty much arrived here at the main event. Here's this for loop, this very substantial for loop here. The responsibility of this for loop is to do pretty much all the work we were discussing earlier, where we were advancing the black pointer steadily, and as we did, we'd examine what the black arrow was pointing to. If that number was less than or equal to the pivot, then what we did was to advance the red arrow and then swap what the red arrow and the black arrow were pointing to. Okay? So you should be very clear about that. I'm presuming that you went through that example carefully enough to really get that. Okay, so now you should be able to compare that with this code here and convince yourself this code is doing the right thing. All right, with the caveat that we are only trying to sort the portion of the array from position left to position right. So we want that black arrow to begin at position left, and we want it to continue and increment until it gets to position right. Okay, well again, J is playing the role of that black arrow. Okay, so we initialize J to the left. It's pointing to the start of the portion that we're trying to sort. It's going to increment each time through the for loop, and it's going to continue as long as J is less than or equal to right. Okay, because we want to quit when we get to the end of the portion from left to right. Okay, each time through the loop, the entry at position J is going to get compared to the pivot. If the entry at position J is less than or equal to the pivot, then we want to increment I, basically advancing the red pointer. Okay, we increment I, advance the red pointer, and after that we swap what's in position I with what's in position J. Okay? Now be careful about this. If you've had the proper background, you should realize the difference between plus plus I and I plus plus. Okay? We're using plus plus I in this third statement here because we want to increment I before using I. Okay? This is the idea that we want to advance the red arrow before using the entry at that position. Okay? So this increments I, and then whatever the value of I is after the increment, that's used to index into array. That's copied into temp. Then what's in position J gets copied into position I, and then what's in temp gets copied to position J. So positions I and J get swapped, but only after incrementing I. Okay, that's a mouthful. That's quite a bit to think about, and I hope you will. You really hopefully come to terms with the details of this. All right, but that is the hard part. After this for loop, everything from position left up to position I will be less than or equal to the pivot. Everything after that up to position right is going to be greater than the pivot. Okay? Now there's one more observation to be made here. The entry at position I is going to be exactly equal to the pivot. If you're skeptical about that, you might go back and look at the example that we did with the figures. The very last swap that took place put the pivot, which used to be at the far right, it put it in, at the end of the first portion, so at position I. Okay? Because the pivot is at position I, it's actually guaranteed to be where it belongs. Okay, the pivot is in position I, and that's where it should be. Okay, so now all that remains to be done is to take everything from position left to position I minus 1, make a recursive call to Quicksort to sort that part, and then take everything from position I plus 1 to position right and sort that part. And once we're done with those two recursive calls to Quicksort, the entire section from position left to position right will be sorted. The bullets in the next several slides just repeat things that I've already explained while we were looking at the Quicksort code. So let me just proceed quietly through these. As usual, as you know, the sorting code provided at the course site in C++ and Java versions includes this Quicksort code. So if you haven't done so already, I urge you to get that code and get it working and running. We'll be doing a comparison of the different sorting methods pretty soon. And at that point, I really want you to have this code up and running. When you're ready, as usual, take the self-quiz.